The goal of this video is to help you with absolute value equations in both 1 and 2 variables, and absolute value inequalities. So we'll take a look at a variety of problems here. The main principle behind solving an absolute value equation or inequality is that once you've isolated the absolute value lump, as we have here, this is an expression that's trapped inside an absolute value sign, and we've isolated it. In other words, it's that equals some other stuff. Once you have that, then you can make the following statement. You can say that this, whatever's trapped inside that absolute value, must be either equal to 7 or negative 7. And let's think about what that means. So either the 2n minus 5 equals negative 7, in which case when you take the absolute value of it, it equals 7. So that makes sense. Or 2n minus 5 is already positive, and when you take the absolute value of it, it doesn't change at all. So you get two linear equations that no longer have the absolute value sign on them. And you can solve them independently and get two answers. And of course, when we're done, we should always check that our answers work in the original equation. So let's add 5 to both sides, and that's going to give us 2n equals negative 2. Divide each side by 2, divide by 2, and we're going to get n equals negative 1. So n equals negative 1 is a possibility, and when we add 5 to both sides up here, we're going to get a slightly different result. We're going to get 2n equals 12, and that means, of course, that n equals 6. So we should check that both of these are valid. So if we take n equals 1 and put it in the original equation, we're going to get the absolute value of 2 times 1 minus 5. And we're asking, does that in fact equal 7? So 2 times 1 is 2, minus 5 is negative, this is 2 times negative 1. I thought I'd blown it for a moment. So 2 times negative 1 is negative 2 minus 5. And of course, negative 2 minus 5 is negative 7. But the absolute value of negative 7 does in fact equal 7. So that one works. And of course, you can look at 6, and let's plug this in our heads because I want to leave a little room for the graph. But 2 times 6 is 12. 12 minus 5 is 7. Absolute value of 7 is 7. So in fact, this one works as well. So let's take a look. We should be able to graph our results on the number line. And of course, what we have is negative 1, 1, 2, 3, 4, 5, 6. So we have 6 over here. And of course, if we're going to graph our solution set, it's going to be this point and this point. And you can also simply say that you have for the answers n equals negative 1 or 6. And that's going to be a valid solution. So let's take a look at some other problems. So here's one more problem, and we're going to go through the same kinds of steps. We have to isolate the absolute value sign. So we're going to subtract 4 from each side to start with. Subtract 4. And we're going to get 3 times this absolute value lump must equal what's that going to give us? 9. We're going to divide each side by 3, and that's going to tell us that this absolute value lump, 5n plus 1, has to equal 3. And then, of course, we can split it into our two statements. So either 5n plus 1 equals negative 3, or 5n plus 1 equals 3, because those are the only two things that it could equal to get that absolute value result. Subtract 1 from each side, and we're going to get 5n equals negative 4. Divide each side by 5, and we're going to get n equals -4/5. Or subtract 1 from each side, and we're going to get 5n equals 2. Divide each side by 5, and we're going to get n equals 2/5. Now, of course, these are a little harder to plug in, but not particularly, since n is being multiplied by 5 in the original equation. So let's look at 2/5 in the original equation. We're going to get 4 plus 3 times the absolute value of 5 times 2/5. 5 times 2/5 is 2. 2 plus 1 is 3. The absolute value of 3 is 3. 3 times 3 is 9. 9 plus 4 is 13. So we've verified that this one works. And you can do a similar step with the -4/5. And you'll find that -4/5 times 5 is -4. -4 plus 1 is -3. Absolute value of -3 is 3. 3 times 3 is 9. Plus 4 is 13 again. So these both work. All right, let's go on to look at some other. So here we've got the situation where we have inequalities with absolute values, and let's explore what's going on here. So if we look at the left side, what we're saying is the absolute value of n is less than or equal to 4. What that means is if n is positive, it must be somewhere between 0 and 4. But if n is negative, it must be somewhere between 0 and -4, because if you went further negative and took the absolute value of it, it would be bigger than 4. So you can view this as n being trapped within the range of 4 and -4. How can we look at that piecemeal in our typical way of breaking this apart? What we can do is we can say for n less than 0, then n must be greater than or equal to. Remember, we switched the sign direction in an inequality when we're multiplying by -1. And so what we've essentially said is if n is negative, then the opposite of n, if n is negative, then it must be greater than -4, greater than or equal to -4. So whenever n is less than 0, so example, if n is -1, the absolute value of -1 is less than 4. If n is -8, that's not allowed. So it's not allowed to be less than -4, because if -8 is less than -4, and so -8, the absolute value of -8 is 8, and 8 is not less than or equal to 4. So this idea that when we split it apart for the case where n is greater than or equal to 0, and I typically write greater than or equal to on the positive side because it doesn't matter whether you include 0 or not as in either of these. 0 is an option, and of course n equaling 0 is a possibility here. So what this says then is when you take the absolute value of n, if it's greater than 0, you haven't changed the sign of it. So think of the left side that we've done here. Think of this side over here as saying, oh, if n is less than 0, then the absolute value of n changes the sign on it back to positive, right? So what we've done is if we want to look at n without the absolute value sign on it, then we've essentially multiplied both sides by -1. Whereas on the right-hand side, if n is greater than 0, when you take the absolute value of it, it does not change the sign of whatever n is if you were to find the values. So what that simply means then, if n is greater than 0, okay, greater than or equal to 0, then n must be less than or equal to 4. What does this look like on the number line? Well, of course, what we're really saying is that n is trapped between 4 and -4. And this should be graphed in the following way. Since this is less than or equal to, we put in solid circles. That means it includes 4 and -4. And it's all values between -4 and 4. So let's look at this slightly different case over to the right. What this says is the absolute value of n minus 3. So this expression, instead of just n, has to be less than or equal to 4. So let's do the same idea, which basically says if n minus 3 is less than 0, then what we have is that n minus 3, that when you take the absolute value of it, you get the opposite of it. So you wind up getting the opposite of n plus 3, and that should be, so n minus 3 should be greater than negative 4. In other words, the opposite things are happening, and we've switched to signs again. And this one is simply, and the other split is saying when n minus 3 is greater than 0, greater than or equal to 0 will do, then n minus 3 must be less than or equal to positive 4. So now we have two inequalities to solve. We add 3 to both sides and we get n is greater than or equal to negative 1. And we say on this side, add 3 to both sides, n is less than or equal to 7. What does that look like on the number line? Well, obviously now n is trapped between negative 1 and 7. I should have spaced them differently, but you get the idea. And if we draw this, we have this. And of course, it's always useful to sort of check to see if these answers work. So if we picked, let's say, something on this number line between here, let's pick n equals 2. So if n equals 2, go back to the original inequality, and then you get the absolute value of 2 minus 3 is the absolute value of negative 1, which is 1, which is less than or equal to 4, and so that works. Okay, so we found in this section of the number line where the values are correct. And you can check this for yourself, check another couple of them to see what we've got. So here are very similar problems, but the opposite case. Now we have the absolute value of n is greater than 4, and this, of course, is going to split us up again into the two cases. If n is less than 0, okay, then, so for n less than 0, then what we have is that in order to take the absolute value of n then and have that result be greater than 4, n must be less than or equal to negative 4. In other words, n must be negative 5, negative 6, negative 7, etc. Something like that, or negative 1000.4. And then for the case where n is greater than or equal to 0, absolute valuatizing it does not change the value of n that you've plugged in, and therefore n must be greater than 4 as well. So excuse me while I fix this a little bit, because of course I used greater than without greater than or equal to, and so this should just be less than. So what does this look like on the number line? Well, what this means is n must be less than negative 4 or greater than 4. So what we're finding is that, and we'll put an open circle, all the n's from negative 4 on down, not including negative 4, work, and all the n's, all the solutions, all the values from 4 and above, not including 4, will satisfy this inequality. Let's quickly go through this one on the right, and we're going to get a very similar idea, where when the expression n plus 3 is less than 0, then n plus 3 must be less than negative 5 for you to take the absolute value of it and have it be bigger than 5. So in other words, n plus 3 must be negative 6 or negative 10 or negative 1,000,000 or something like that. And of course on the right hand side when n plus 3 is positive. So what we get is n plus 3 has to be greater than 5. So we get these OR statements of course, subtracting 3 from both sides gives us n has to be less than -8. And we get over here, I'm sorry, this should be 5. I'm not sure where I wrote 0. When we subtract 3 from both sides, we're going to get n has to be greater than 2. This looks like the following on the number line. And here's -8, and here's 2. And what we're going to get is an open circle and this. So everything below -8 works, and we'll check that in just a moment. And everything above 2 works. So what that means is we could check, does, for example, -10 work? And if we plug -10 in for n, we get -10 plus 3 is -7. The absolute value of -7, excuse me, is 7, and 7 is indeed greater than 5. So over here, that looks like this section works, and we can test, let's say 5. 5 plus 3 is 8. Absolute value of 8 is 8. 8 is greater than 5, so over here works. Okay, let's take a look at some more challenging problems. So here's a slightly more challenging example, but exactly as we had done with the equation problems before, you simply want to solve this as if it's an equality, isolate the absolute value sign, and then go through the same reasoning we've done on the last 2 slides. So of course what that means is we're going to add 3 to both sides, and we're going to get 9 times the absolute value of n plus 1 must be less than or equal to 45. Then we're going to divide each side by 9, and notice we're dividing by a positive number, so we're not changing the sign at all, the direction of the inequality. So we're going to get the absolute value of n plus 1 is less than or equal to 5. And now we split it into our 2 cases. So if n plus 1, if the absolute value of n plus 1 is less than or equal to 5, then that means n plus 1 itself, if negative, I'm just going to write if negative, in other words, if n plus 1 is negative or less than 0, then n plus 1 itself must be greater than or equal to -5 for that to be the case. For example, if n plus 1 is -4, it's greater than or equal to -5, and the absolute value of -4 is 4, and that's less than or equal to 5. So if it's negative, this is the case, which means, of course, then n has to be greater than or equal to -6, subtracting 1 on each side. And over here is if positive, we're going to get the case of n plus 1 then having to be trapped inside 5. In other words, the absolute value of n plus 1 in this case, or n plus 1 in this case, is trapped between 5 and -5 on the number line. So what does that mean for n? Well, there's a little bit of a shift because of the subtracting 1 from each side, and we're going to get n has to be less than or equal to 4. So on the number line, this is going to look like this. We're going to be -6 down here, and we're going to be 4 here. And what we're going to get is, and this will be filled in circles since it includes the values, and every value in here will satisfy the original inequality. So you can check this for yourself. Plugging in 0 would be useful. Everything between -6 and 4 on the number line should work. So we plug in 0. 0 plus 1 is 1. Absolute value of 1 is 1. 9 times 1 is 9. 9 minus 3 is 6. 6 is indeed less than or equal to 42. So 0 works, and we could try a number of other numbers. But for example, it would be worth trying 5, because that's out here. If we look at this, if we try 5, 5 is out here. Okay, and should not work according to our conclusion. So let's check it. If we put in 5 for n, 5 plus 1 is 6. 9, absolute value of 6 is 6. 9 times 6 is 54. 54 minus 3 is 51, which is not less than or equal to 42. And you could also find that something less than -6, like -10, does not work. Okay, let's move on to looking at inequalities in 2 variables. So here's a problem that is an absolute value equality in two variables, meaning that it's going to be graphed in the coordinate plane, which means that to graph it, we're looking for solutions that are ordered pairs that make this equation true. I've given an input-output table over to the right to save a little bit of time, but you can test these numbers for yourself. And what you'll see is this interesting effect that right here, that's the lowest value y can ever be in this equation. And of course that's fairly obvious when you think about it. You're taking the absolute value of some stuff, x minus 2, and when you take the absolute value of it, it can never be negative. So when x minus 2 equals 0, we get the interesting effect that that's the bottom of this graph. And if we were to sketch this graph quickly, it would look something like this. Let's say that's 1, 2, so there's 2. And you would get a graph that looks, let's draw it in green, something like this. Now, what we're saying then is for the case for when x minus 2 is less than 0, when you take the absolute value of it, it must become a positive number. But it has to equal the same size as y. And so it must then give you x minus 2 equaling the opposite of y. Because then when you take the absolute value of it, you're going to get the positive version. Okay? So what we're saying is y is always a positive number. When we take the absolute value of x minus 2, that's a negative number. X minus 2 is a negative number. So x minus 2 must be equal to the size of y in the negative direction. So this provides the left-hand graph. And so let me just make a little line over to here. That's the left-hand side of this. So this graph is going to have a vertex at x equals 2. And so whenever x is less than 2, the graph applies, this linear equation applies, this one right here applies, because it's going to give us a value that's the opposite of y, and when we take the absolute value of that, we get y. And so, for example, if x is 0, 0 minus 2 is negative 2. The absolute and negative 2, the absolute value of that is 2, so y is 2. But without the absolute value sign, x minus 2 is negative, and therefore it must be the opposite of that value of y that makes this equation true. So we also have the case when x minus 2 is greater than 0, then when you take the absolute value of it, it doesn't change it at all. So that means x minus 2 must equal y instead of the opposite of y. And that's going to give us the equation on the graph, the linear graph on the right-hand side. So what we've done is we split it into these two equations. Now, of course, both of these equations, when x minus 2 equals 0, should actually give us the same value, and they do. If you check this, you can see this for yourself. So when you plug in 2 for x, because that's, of course, when x minus 2 equals 0. So when you plug in 2 for x, you get 0 equals 0 in both cases. Now this looks a little more complicated if we look at a tougher equation. So let's move on to another one. So here's a slightly more complicated equality in two variables. And so what we have to do is go through our convention of subtracting 4 from each side to isolate our absolute value. So we have 2x minus 6. The absolute value of 2x minus 6 equals y minus 4. Now, once again, if 2x minus 6 is less than 0 for all the values of x, such that 2x minus 6 is less than 0, when we take the absolute value of it, we will change its sign. So what that means is when 2x minus 6 is less than 0, 2x minus 6 equals the opposite of y plus 4. I've taken the opposite of the entire right side. So, and that means we need to take the opposite of positive y, and we need to take the opposite of negative 4. So, solving this correctly, we're going to subtract 4 from each side. Subtract 4 from each side. That's going to give us 2x minus 10 equals the opposite of y, and therefore y equals negative 2x plus 10. So that's going to be the left portion of this graph. And on the right hand side, we're going to graph 2x minus 6 equals y minus 4, because when this is for the case where 2x minus 6 is greater than 0. And that solves pretty quickly as y equals 2x minus 2 from adding 4 to both sides. And this is going to give us, if we graph this carefully, this is going to give us a graph that looks like this. Now, what that means is we're looking at the crucial place where this graph must bounce, where y has its lowest value. And so we can actually look and say, let's go back to the original equation. When the absolute value of 2x minus 6 up here at the top is 0, that's got to be the lowest that y can be, because if 2x minus 6 is anything other than 0, when you take the absolute value, you get a positive number. So then it would just be bigger than 4. So the question is, when is 2x minus 6 equal to 0? Because that's going to be the bottom. So 2x minus 6 is equal to 0, of course, when x equals 3, because 2 times 3 equals 6 minus 6. So we know that at x equals 3, so at x equals 3, we know that y is going to have a value of 4, if we can plug that into our original one. So what we get is our vertex of right here, the bottom point of 3, 4. And then, of course, we're going to get linear equations to the right, and that linear equation is going to be matched over here. And we're going to graph this guy here. Now, of course, it's only valid up to that point. Each of them is only valid to the level where x equals 3. So when x is less than 3, this equation is valid. And when x is greater than 3, this equation is valid. And when they're 3, each of them should be true. So let's double check that we get 3, 4 from each of these individual equations. So 2 times 3 is 6, 6 minus 2 is 4, and we get 3, 4. So I've put a blue check mark there prematurely, but there you get the idea. And if we put in 3 over here in this spot, if we put in 3 there, that's 2. Negative 2 times 3 is negative 6. Negative 6 plus 10 is 4. So in fact, we do get 3, 4 for both of them. So what you really realize is that this line would continue that direction, and of course, when you go in the upward direction, it's going to have a y-intercept of 0, 10. And this one would have a y-intercept of 0, negative 2 if you were to continue, if it were valid in this area. But what we actually have for the graph then is this equation here, where it bounces at the the point 3 comma 4. I hope this has made it a little clearer what's going on, but remember, you're always getting the vertex of this V, and that's whenever the absolute value sign is being is positive. If there was a minus sign outside here, if it was negative out here, then you would actually get a mountain. You would get two lines that come up to meet at a point and go back down. So they would have a peak instead of a valley. So right now we have a valley at 3 comma 4. And that's because the valley, the lowest value of y is when the absolute value of 2x minus 6 is 0. If you think about if there was a minus sign out here in front, where I've circled with the yellow line, if that was negative, then 4 would be the biggest value of y, because every absolute value of 2x minus 6 is going to be positive, and when you take the opposite of that, you're subtracting something from 4, and so then you'd have a mountain. So that would be a peak instead of a valley. I hope this has helped.